Okay, I guess we can start. So a little bit of a deja vu, obviously after the break, no one wants to come back. All right, and I see some familiar faces, which I'm really glad that you survived. That's very cool. Welcome. So yeah, welcome everyone to this. It's operating systems, right? cs5460, 6460. A mixed graduate undergraduate class, right? So today our plan is to first go over the class logistics, essentially figure out what's coming, how hard it will be, what to be afraid of, what not to be afraid of. And then I will try to motivate a little bit why would you do this class, right? So because we're going to talk a little bit about it soon, but we roughly have like 50 undergraduates and 100 something graduate students here. So like obviously it's better to understand why we're doing it, right? So question number one, do you guys hear me well in the back? I'm reasonably loud, but I can also there is a speaker right here, and I can bring like a portable speaker if needed. So just let me know. Again, nothing to be worried about in the first week of classes. No homeworks, nothing, right? So just a landing pads for everyone to be able to do it. So by the way, so you probably noticed that I enabled live streaming, right? So I will be streaming the class on YouTube. Why YouTube? YouTube is a convenient storage versus like review mechanism, right? So I could have, and I used to do it in the past. So I was just recording with Zoom, but then Zoom tries to delete my videos, right, and stuff like that. And University of Utah at the moment does not provide a service which would allow me to archive my videos for at least a year, or ideally for several years. And the reason we are recording, because first of all, you guys will be able to review anytime. And second, there are people who actually watching through the class, like some random people from all over the world, once in a while show up and like just say, okay, I was going through this class, I like it, let's do this. And every year it changes a little bit, so it's convenient to have everything recorded. That said, what it means is that technically speaking, you don't have to be present here, although I do encourage people to be present here, right? Why? Because success of this class largely depends on you, right? So I can lecture, but my lecturing is just one version of what needs to be taught, right? So I have my own line, but you might be somewhere off to the side, right? And if you ask me questions, then I can converge towards your understanding and like improve my style as well, right? So it's nice to have people talking in the class, and I will be talking to you a lot. And also, I'll cover it in a second. In the end, you have to watch it live to participate in the class to get like certain credit. Okay. Actually, like I hope that live stream works. It's easy to screw up the first time, but we'll see it soon. Okay. So a little bit of an introduction, right? So I'm obviously a faculty here at the School of Computing, and the bit which is most interesting about me is that I actually build operating systems, right? Since I was a student like you. So I was, roughly 18 when I started building first operating system, which I thought will like move my career and move the world forward. Didn't happen, but still, like I built something and I learned something and stuff like that. So what it gives you is it's kind of, in a way, a unique position, because a person who does something and teach the same subject is usually a better teacher. I'm okay-ish, right? So I'm not saying that I'm great, right? But I'm trying to be good. But at least I have the background knowledge, right? So which also has like a couple of advantages and disadvantages. Advantage is that yes, there is knowledge there, and we will go and I will kind of like I hold your hand and I walk you through the operating systems. But it will be a little harder than a regular class. So why is that? No, because I naturally that's my area. I'm really enthusiastic about it. I wanna see an operating system designer in every one of you, right? So that's my goal. And whoever doesn't like it, it's okay too. I will still help you as much as I can, right? And so that's kind of the advantage. The disadvantage is that it tends to be a little harder than a regular, let's take a book, go through the book class, right? But I promise that it will be totally doable. So myself, I built, like I said, a couple of operating systems. You can always click on the web page. Should probably update it, but there will be a group web page where we'll like keep track of what we're working right now. So, but like we really build new operating systems, me and my students, right? Which is kind of fun for us. What does it mean in terms of this class, right? So as I said, we have roughly 150 people, 50 undergrads, 100 grads. Each year, the composition of the class changes. I don't know, last time we had maybe 100 undergrads and 50 grads. Maybe it's a change in requirements, I don't know. But how many of this class is a required class? So, and are you graduate students or undergrads? Graduates. So for graduates, it's required class that they have to teach. Anyway, so in any point of time, most of the information will be available on the class web page. Right now, there is still mostly nothing, right? So there will be a link to all this. By the way, let's update the page. It's like, no, it's still last year. I'll do update like this. Yeah, cool. So this is this year, spring 2024. What will happen here is that we will have a schedule, right? So with every lecture for every week, right? So today's lecture is logistics. I will provide a link to the slides, and I will provide a link to the video, which we recorded, right? So you can come back always and review the lecture, right? Later on. And if you're curious about what really will happen in this class at the level of details, you can always click on a previous version of this class. Last time it was taught here by me last spring, right? So, and essentially here you have the complete full schedule. So logistics, introduction, operating system interfaces, homeworks, everything is kind of open. So I'm not saying it will be the same. So I tend to change the class because I take your feedback, right? So because every time you write me a review, by the end of the year, I say like, okay, I was wrong in this, and this, and I will change it, right? So, but there will be everything like homeworks, and again, like there will be a set final exam date. And if you're curious about what the exams will look like, there's a list of previous exams as well. And everything is again open. Wow. If URL is correct, right? So, so what is wrong here? Probably this. So we'll patch the URLs a little, right? But this is essentially what we've done, or what we did. Like, it's probably from 2 years ago, but I will update from the last year's exam as well, right? So, so again, like the open nature of this hopefully will help you, right? So what it means, what I wanted to say here, I forgot. Everything is recorded, so everything is available. So if we go to the current version, you can always even click on a class repo and submit me a pull request. So essentially, if you feel like I made a mistake in the lecture or something is broken in the homework, and it happened in the past. So if you like look at the like how many contributors, like it's a ton of people. So not everyone was a TA. So some of these people are students. So essentially, people do submit pull requests, and I will try to reflect and fix whatever is broken there, right? So majority, like takeaway. So majority of the information is available, will be available on the class webpage. Agree? Any questions? Okay, let me go forward a little bit. So okay, so what is this class about? Again, my goal, I actually assume that you have almost zero background knowledge about operating systems, right? So which is in like maybe 99% chance is true, right? So because there might be a couple of people who did something in the past, but most people who didn't, right? And so what we're gonna do is that we gonna look at one simple implementation of an operating system. So my class originally was inspired by this class from MIT. So it's operating system engineering. The first time I taught this class, I was really like a big fan of this version of this MIT's class. You can always click here, and they do teach it as well, and they do modify it. So I linked version from 2018, which I believe is the most maybe closest to what we have. And at a high level, the idea was to teach operating systems by doing, right? So what it means, again, don't just open the book and say, look, there's a chapter which explains what a process is, what memory is, virtualization memory. I can explain you what it means in my lectures, but in the end, I will ask you to look, there is a concrete implementation of this, let's say, a subsystem which virtualizes memory. And I will ask you to do a simple modification to it, right? And by doing this, I will force you to read the source code of this small operating system, which we'll be using in this class. And it's called actually x86. So x86 is it's a simple Unix-like kernel. It's surprisingly powerful, and it's also surprisingly close to what we actually running on our machines today, because like almost every one of you has a Unix in your pocket. So you have to be very, very careful not to have one, because Android is running Linux kernel, Mac OS, which I started running on my laptop. I used to run Linux. Runs a version of FreeBSD on top of another microkernel, right? But it's essentially the same Unix architecture. iOS, actually, don't know exactly how iOS works, but guessing it's Unix as well. Windows is not Unix. That's funny, right? So if you run Windows and you have a Windows phone, which is highly unlikely, right, at this point, you don't have Unix in your pocket, but everyone else does. So what is it I'm saying? I'm saying that this x86, x86 is a tiny Unix kernel. So essentially, I will ask you to build like extensions to it, system calls. And it's very small. It's only 9,000 lines of code. So it's kind of feasible to read almost entire 9,000 lines over the course of the semester, right? And yet it captures kind of the state of the art in operating systems. I mean, let's say in commodity operating systems, which are run today. So if you ever decide to make a change to a Linux kernel, at least you will understand what it's doing, because it's doing kind of similar things to what this x86 is doing, right? So this is kind of an interesting, it's a very useful way of teaching. You say, look, here's a playground. It's reasonably small, but it's very, very realistic. It has quirks, like if you make a mistake, it crashes. So it's not like we'll run it in a QEMU simulator, but it actually boots on real hardware. And as maybe like an extra credit, I will ask you to boot it. It becomes harder and harder to boot every year because of how the boot protocol is implemented on modern machines. But on the 5 years ago, it was trivial, put the USB stick in your machine and it actually boots. So anyway, so that's the plan. So real operating system. So, there's a couple of good things about it. So first of all, MIT people wrote a book about it. It's openly available online. So written by a couple of professors at MIT, and Russ Cox. Russ Cox, I think, is an engineer at Google now, who probably was a PhD student back then at MIT, right? So it essentially goes and explains you the architecture of this system. So for example, if you go to this traps chapter, which we'll cover later in the class, right? So it will explain what it means to handle a system, to handle an interrupt, to implement a system call, and what it will do. It will essentially explain it at the level of details, like what is there in the specific register. And it will also have links to the source code. So essentially, let me just find one. So something like this. So it says, okay, the function trap, let me just zoom in for a sec, is actually at line 3319. And the way this kernel is written, I mean, the style, the actually coding style might look a little bit unusual to you. They use very short names. They use very, I think it's 2 spaces of indent. And that's done to be able to fit the source code on a PDF, essentially. And let me just show you how it looks. So remember trap 3319, right? So we go back to my slide deck, for example, here, and this is the source code printout. And I can say, look, what was the number? 3219, something along those lines. No, wrong. Which one? 33. Yeah. And yeah, so first of all, yeah, sorry, couple of it. No, let's, yeah. So this is a printout. It happened to be a piece of assembly. Let me just zoom in again. Which it's assembly instruction call, which calls the function trap, right? Mm-hmm. So they probably in the description, they were actually referring not to a function implementation, but rather to a function reference, right? And you say, look, wow, I'm not saying that you have to use this printout to read the source code. You can use any tool, right? So Visual Studio Code works pretty good, right? These days, I use my whatever Vim editor, but essentially the whole kernel can be printed, right? And it's convenient. So if we search a little bit more here, where is it? What I wanted to show you. So this is specifically the function trap, which I was referring to, right? And they say, look, by the way, guys, so it's implemented at line 3401, and it's referenced at those other lines, right? So if we go to this line, 3401, am I correct? Where is it? Oh, search. So this is an actual implementation of trap, right? And so it's implemented in C, right? So which by extension means that the only prerequisite for this class is the ability to read and code in C. It's actually a little harder these days than it sounds, right? But that's everything else I will explain. And plus to work with the shell, like a little bit of background with shell, right? So if you completely don't can't read C, then you should either quickly read a book about it and learn, or you should reconsider taking it. It will get hard because essentially I will ask you, okay, look, guys, somewhere in this function, you have to make a change. And I will not tell you where, I will just tell you semantically. Maybe you will check for a specific system call and do something, right? So you have to understand what this function is doing. I will cover it in class. So the way I will teach, I will first introduce a high-level concept of what trap is, right? And then I will go through the source code saying, okay, we enter here, we understand what this first argument is. It's a trap frame. It's like essentially registers which the operating system saved when it entered the privileged mode of execution. The trap number is in that field. If it's a syscall, then we check for some conditions, whether the process is still alive, and return if it's true, and handle other interrupts. And if we really like up to the handle a system call, we eventually go where? Where is my system call handling? Should be somewhere. Maybe in that switch statement. I already forgot. Trap number, syscall. Cannot find it. You see it? Ah, no, hold on. We handle it here. I apologize. So essentially you enter into this function. So I will explain it at this level of detail, but you still will have to follow, right? So to be able to follow and then kind of understand how to do modifications in C. Okay, part of what's coming, right? Any questions? Again, I will stop here. Yeah.
So you said we only run the x86 on the QEMU, right? Not on the hardware.
Right. So the question was, how are we going to run this operating system? We're going to run it on top of something what is called a virtual machine, right? So everyone knows what it is. We'll be one step closer. QEMU is specifically what it does is it emulates an x86 hardware, right? So to the point that it can boot an operating system. And later on, I will explain bits of internals of how QEMU works. It's actually much simpler than you think, right? So, I mean, maybe you know already, right? But it's not as hard. So it looks like rocket science, but in practice, I mean, if you survive this class, and most likely I will teach advanced operating systems next semester, right, in fall. And then maybe we will do something with QEMU, right? Actually, or build a tiny virtual machine ourselves, because it's not really it's not that hard. If someone helps you, right? It's like with mathematics, proofs are super hard. I used to be I was not a mathematician, but when I studied mathematics as a student, right, before switching to computer science, and so like really there it was hard, and someone has to help you. And if someone helps you, then you're good, right? If you're putting in effort. Okay, any other questions? Yeah.
Will we also touch the Linux source code?
Linux syscalls, not really. They are hard. In this advanced class next semester, I can talk to you, like I can explain every instruction of the Linux system call handling, but it will be too hard to do it in this class. Even this one, you will see how like it builds up fast because it's very concrete. So you drop one flag somewhere and it doesn't work, right? So you need to know everything. But again, I can usually explain. Other questions? Good. Okay. So again, the point is like it looks a little, as I said, like two spaces, full codes with two spaces, right? Very short names. Like I guess on your job interviews, the trap frame would be trap_frame, right? So here it's TF, but you can get used to it, right? So this coding style eventually grows on you. Although a lot of people complain about it, but eventually it's kind of likable. Okay, so we got it. So we have a real kernel, and a book about it. So we'll use a couple of times yet another book, which is also an open source book. This one is written by a couple, Ramsey and Andrea Arpasi-Dussault. They are professors at Wisconsin Medicine. And their book is a little bit more like a classical college style book about something, right? So it's again openly available online from this website as a collection of chapters, right? So if you click here, you'll get a real textbook. We will use it to cover some general operating system concepts, right? Essentially like a process. So sometimes it's nice to read something because reading is yet another form of thinking, right? So when you read, you comprehend knowledge differently. So one thing is a lecture, one is read something about it, right? So, but again, you don't have to buy a book, right? So everything will be available openly. So just a little bit of details how the class will be structured, right? So probably, okay, we'll have like 5 to 6, maybe a little bit more homeworks. Homeworks will be, as I said, assignments which will require you to code something. And you're very welcome to look at the schedule from the previous year, click. There are like very detailed descriptions of what's going on in the homeworks, but at a high level, it's something like do something with a makefile, because again, I assume that maybe you know something about makefiles, but maybe you don't. And if you don't know anything, then it's a little hard to do anything in this class. So that like maybe first homework assignment will be something like do something with a makefile. Then there's another way of complexity here. It's a little bit hard to debug operating systems, right? And so there will be some kind of an assignment of, let's take a GDB, which is a GNU debugger, which is an infrastructure which is kind of tuned to debug operating system kernels. I'm pretty sure you can connect a Visual Studio to it, but it might be a little harder. So, but GDB, and it's useful to kind of learn this tool. So there will be an assignment on that. Maybe we'll build like something like a loader, which loads the program in memory. But don't get scared. Again, I will explain what needs to happen, how it works. So, and assignments, they will be kind of lengthy. So there's a lot of text. You have to read through it, understand what needs to be done. Usually the actual code is relatively small. Sometimes it's like maybe 50 lines of code, but it takes you 2 weeks to write this 50 lines of code. But we're going to help you. Again, we have good TAs. Again, locked out this year. So the TAs who you have took this class before, they're actually interested in operating systems as well. They either work or used to work for me. So they're kind of knowledgeable people. They will help you. Like you say, okay, I don't know how to do it. And I will help you. Come to my office. Like, here's my code. I don't understand. I will sit with you, debug it with GDB, help you to build it, right? And there will be a little bit of biggish assignments, kind of like build a shell. Sorry, to highlight, implement a system call for this x86, maybe do something with the memory subsystem. Maybe it was a file system as well, right? So again, homeworks, no homeworks this week. No need to be scared. You don't have to do anything this week, but I still appreciate that you came. Right? So here, because I have to cover right, and teach, and it will be lonely if you're not here. So again, so like you probably just today you just came for this one line here, like this bullet, which tells you like how you will grade it, right? So this year it will be 40% of your grade will be homeworks. New this year, participation, because at some point, people tend to disappear. And so participation will be some kind of a quiz in class. Yet to figure out how to do it. And if you have ideas, you can tell me. So, but most likely some kind of an online tool in which I ask a question, you answer it live, and then it gets recorded, right? And so overall, like over how many weeks we have, roughly 20 lectures, right? So you will get this participation credit. There is yet another bit, quizzes, right? So every week, or almost every week, there will be a quiz, which will be assigned by the end of the week. We used to assign it as you have like, you don't know what will be on the quiz, like just material which was covered during this week, right? And then I'll give you like 45 minutes to answer questions. Well, it was super stressful. People said, okay, like, man, it's too hard. So I think this year it will be, you just have the whole weekend. You open the quiz, you can read up to answer questions. It will not be hard, I promise. But at least it will keep you kind of in sync with the class, because again, it just evolves too fast at some point. Like, unless you invest your effort regularly, it will become hard. So the quizzes will be a mechanism to essentially help you to be in sync. And then midterm exam and the final exam. There is one specific thing about those midterm and final exams, which some people don't like, and some maybe like the other aspects of it. So what people don't like is that they're relatively hard. And it's not because I'm trying to, actually, I don't want to give you a grade, to be honest. I just want to teach. I would give everyone A, right? So, but university kind of doesn't like this. And so they go after. But I'm not a big fan of grades, right? Because the way we learn usually is just like motivation is elsewhere, not the grade typically. So again, what I'm saying here, so exams tend to be hard. That's to essentially, for me to judge, like it's kind of like taking a photograph, right? So if you overexpose a picture or a photograph, right? I don't know even like, do we know exposure anymore, right? I click and it always works, right? But on an old camera, you can adjust the shutter speed, and if you overexpose, everything is white. So if I make my exam simple, then all of you come as A students, right? And I don't even know who is the best, right? So that's why it's a little bit kind of like proper distribution. So there will be like a median, and like there will be a couple of people at the high end of the curve. But what's good about it is that we're very, very lenient graders. As I said, like everything will be curved like crazy. Like, I don't know. I think it's very hard to get anything below like B- in this class, because C, like I forget how I usually set this grade, but it's almost like if you submit the homeworks, it's C automatically. So something along those lines. So again, don't worry too much about the grade, despite the fact that the class will be hard, right? So just grade is not very important. And it will be structured in such a way that you will get a good grade. It's very hard to fail. And actually, I got softer on the exams over the years as well. Just again, the trauma of failing the exam, it gets to me as well. So I'm not a big fan. So, but what I wanted to say, another thing about the exam is that it's completely open everything. The only forbidden thing is communication. I mean, in the class, right? Or like if we do it in person, or communication asking for help, right? Somewhere like you can do it probably, but that's not allowed. And the third, so like communication asking for help, and the third thing which is not allowed is searching on Google. Why is that? Because it's just that the answers which I get are hilarious, right? So if you like ChatGPT and then I have to grade it, well, it's not fun, to be honest. So the answer should be your original, but everything what we like, all the lectures, books, your notes, any tools which you want to use, GDB, source reading tools, everything is allowed. In fact, the machine will be in front of you, right? So most likely the exam, just to avoid printing, it will happen through grade school, right? So you'll just like answer questions, but they will be open-ended questions, right? Typically. So, the reason I'm saying that is that you don't have to remember any of the details. It's kind of like real life. So if you can quickly recover the solution, then you will succeed, right? So any questions? Because that's, again, probably the most important part of it.
You say quiz will be assigned at the end of the week. Be assigned on the Thursday, beginning of Friday, end of Friday.
Wow, let's say Friday night, but I tend to be late. I mean, and I will allow you to be late, but I will try to be on time as well. But roughly end of like Friday night, you maybe Monday night or something. So just if you have to go out for a weekend, you still have Monday, right? And you can always email me and say, okay, I have this and this event, and I like get an extension. We'll figure it out. But we'll see. Yeah.
Do we need to be in person for lectures, or can we be doing the lecture?
Well, yeah, you can be on live stream. I mean, it hurts everyone because if the room is empty, it's less fun to teach, to be honest. So if you can, please show up. And partially this participation credit is, and okay, we'll have to probably figure out a way for people. I was thinking to ask questions offline, but maybe it's too hard. So in practice, it's very, very hard to enable the infrastructure, which would allow you to ask questions during the class, right? But you can be offline. So you can take the entire class offline, probably showing up only for the exams, in-person exams, if we decide to make them in person, most likely, right? But again, I would really appreciate if people show up and participate in class. Any other questions? Yeah.
For the exam, you said it's open book, right?
Yeah.
So could we also use our laptop to get online?
Yeah, totally. But I will ask my TAs to walk around and enforce the fact that you don't use like Google, ChatGPT, stuff like that. Again, because the only reason I used to allow it, but then I get just some random answers, like a person Googles something on Google and just says, okay, I'll just copy paste and you create and give me some partial credit. And it's hard to argue against it, right? So that's why we said, okay, let's not do it. Just otherwise the exams look like funky.
So about the
Yes. Right. Yeah, immediately after the first day. It just simplifies accounting for us because we don't have infrastructure to yeah. But again, yeah, it's a sharp penalty, but you still can catch up, right? Because there will be also some extra credit assignments or parts of the assignments. And also it's not uncommon that I give extensions. So if it's really, really hard, we will remove it if majority of the people are late. Any other? Yeah.
About homework, about what kind of platform or OS should we use in our own machine, or do you provide some machines?
Right. So it changes actually from year to year because School of Computing gradually kind of like changes their infrastructure. And last year, it wasn't actually kind of fun. So we kind of failed to set it up in such a way that it's convenient for you. We'll try to do better this time. So we usually provide the infrastructure on School of Computing machines, but last year it wasn't ideal. So they required like a lot of like tuning, which was irrelevant to the class, to the like core mission of the assignment, but took some toll essentially of your time. So the way it will work is that people who feel like they're willing to put some effort into setting it up on your own machines, and we will provide instructions, can set it up on your own machines. We will provide infrastructure on School of Computing machines, And finally, the way most of the homeworks will be graded will be through the auto grader, meaning that the end goal for you is to make sure that it passes the tests on the grade scopes auto grader, which uses the image, whatever the, what is it called? The virtual container, which was set up there. Right, but you can submit multiple times. It will always tell you, okay, failed, succeeded, stuff like that. Any other questions? Okay, good. So more or less, we're almost there. So we ask you to submit your own work, right? So, and we'll go after you. So essentially, we have tools which allow us to compare submissions, right? It's not fun at all, like for us, because, you know, catching someone who submitted like 3 versions of the same homework, 3 people. So the rules are the following. You can discuss anything. You can ask things on Piazza, and Piazza will be our engine for essentially asking questions. You can even ask parts of the, like show the parts of the source code, but not the exact solution, right? But then eventually you have to work through your solution yourself, right? If it helps to work in like with your buddies to discuss again, go for it, but just make sure that it's your own work, right? So, and if you, like, I hope we will not have to go after you. So again, so organization of the course, you probably guessed. So essentially I will lecture, they will be live recorded. Reading assignments, let me show you on the web page. So where's my web page? This one. Oh, not this one. Just wanted to. So here today we don't have any reading assignments, but typically after every lecture there will be like a reading assignment, right? So there might be like a real assignment which is compulsory, like this one, chapter from us, operating systems in 3 easy steps, chapter 2 introduction, and an optional reading, a link to a Kernighan Rich's book on the C programming language, right? And so it's not like a lot of reading, but essentially sometimes there will be more, right? So that, again, I will not be explicitly mentioning this in the class. So just check the schedule after every lecture and you will find the assignment there. Yeah, I will. Yeah, I will create Piazza. I will create grade scope, push everything on Canvas. Just forget to mention. So Canvas will be, I mean, I use Canvas essentially just as a mechanism to introduce the assignments and deadlines into your calendar, right? So every actual assignment and a quiz will be announced on Piazza, and it will have a deadline. Oh, sorry, not on Piazza, on Canvas, and it will have a deadline. So, you know, I hope that like most classes use Canvas and you have a single calendar which allows you to track deadlines, right? But these reading assignments will not be. So they will only show up here on the class schedule, and there will be no class schedule on Canvas. It's just too hard to maintain too. Good, but all the quizzes assignments will be there. So, and will be here as well, not like the quizzes, but the homeworks. And there will be announcements on Canvas as well. Okay, homeworks, design redos, like those are essentially part of homeworks or maybe quizzes. And again, I don't think I published the quizzes just because it used to be that we kind of kept them secret, but I think we can just open them up this year as well. So you can answer them. What else is there? One other thing about plagiarism, which I wanted to mention, is that you're not allowed to publish your solutions online. So I wasn't explicit about it, but then like, just because the reason is the following. So when we assign a homework on Shell, I mean, Shell is a very specific piece of software. It does just a very specific thing. And at some point, there is only just a couple of ways to assign Shell. And you probably already had Shell assignments in previous classes, right? So ours will have slightly different focus, but maybe it's largely that we'll just repeat what you already done. But after some number of years, like there are so many submissions of this shell assignment. And I mean, I do change homeworks, actually. If you like backtrack the history of the class, we switch from one shell assignment to another completely, just to make sure that you can start fresh. But there is only so many ways to do it, right? So, and the same with x6, because we'll kind of lock ourselves into this sandbox of x6. This is our playground. At some point, you cannot come up with new homeworks about it, although we do come up, we slightly change them every year, right? But so and some people, what people do is just, let's say, scratch x6, let's just teach a different kernel. But then it gets hard for everyone as well. So yeah, no publishing code. Prerequisites, as I was mentioning before. So the one really hard prerequisite, which is really important in this class, is the ability to read and write C, right? And as this wonderful picture tells us, it's kind of simple, but at the same time, I'm not saying that C is the best language. So by the way, so it's not, unfortunately, but it's easier to teach this class in C. If I ask you a question, why? Can you guess the reason? What is so special about C? What makes it convenient for operating systems, or for building them and then teaching them, I guess? It's a low level, but when you say low level, what does it mean really? Well, memory unsafe is not a good property. It's really, yes, unsafe, but does it help you in any way? I mean, if I were confident in your knowledge, I would teach this class in Rust, right? But Rust is harder because it will drive you nuts before you even start coding, right? C will drive you nuts too, but in a different manner. Okay, you were probably. That's correct. So that's probably one of the best answers which we've heard, because it has like the idea. So C has this, despite being this kind of weird language, C has this property of transparency. So it's so simple that it's almost like assembly. It's almost like you're coding in assembly, but you can read it. Like assembly is harder to read. What it gives you is, it's almost, and this is the skill which we'll be practicing in this class. Like, you see a function like printf, and I can ask you a question. So can you tell me what's going on inside? And with C, you can almost always guess. So if you have a for loop, you almost can see what assembly the compiler will generate. If you have a language like Java or C# or anything like let's say Go, then there are layers of two things. Layers of first programming abstractions, like iterators. Okay, tell me what iterator will be compiled. Well, even for me, it's hard. Sometimes I'm surprised. It is sometimes compiled differently as well. Or some other abstractions, right? Option types or something like that. They are convenient, they're better, they're safe, but they are not transparent. And it's harder to build an OS in those languages. It's possible. And the second thing is that there's the complexity of the runtime. C doesn't have a runtime. So you write a for loop, there will be, a jump backwards or jump forward. So you can guess what's going on. And it's easier to debug, especially when you say, look, I'm loading a process. I'll teach you how to compile the thing, and like how to use the compiler to make sure that your program is linked and loaded in such a manner that it can be loaded at address 0. And if you set the instruction pointer to address 0, it will actually run. So the second language, which is the closest to C, is Rust. And Rust is safe, has programming language abstractions like option types and whatnot, like almost like any other functional programming language. And it's, in general, even has this transparency. So you can always, sometimes guess what it will get compiled to, but it has a very funky type system, right? And then you have to fight against it unless you are an expert. It's called linear types or single ownership. So that's why C. So, and if I say, let's do something in Java, either I will be cheating, I will teach you a version which is almost like an operating system, but it's not. Or if I really force you to run Java on bare metal, then you're in advanced operating system class. So I will show you how to boot into Rust, for example, and it's not super hard. You can boot into C++. I used to do it when I was a student. Now, I don't remember how, but it's probably doable again. But again, just use this mechanism, which makes it easier. And that's why, but it has tons of disadvantages, like from this, like weird syntax to access memory pointers. I didn't have a lecture about it, but I think I should. I will probably change the class in such a manner that we will look at C. I will explain the basics of pointers and memory allocation. And then the fun part about it, that there will be a homework assignment and you will build me a memory allocator, like a malloc. And again, it's very easy. It's so surprisingly easy that you will be amazed that, okay, cool, like I can build malloc. Okay, but what else is required is be able to code in, you have to be able to code in shell, right? I've seen kids finishing this class with no shell knowledge, Visual Studio integrates so well, and I don't mind it. So go for it, as long as there are like pros and cons, right? So, but in general, yeah, you will at least should understand how to like type basic commands in shell and understand what's going on. And you will need some assembly skills, but we'll have some lectures on assembly. So I will introduce x86 assembly. I will probably, maybe you will have to write a couple of lines of assembly, but you will have to be able to read and comprehend, let's say 100 or 200 lines of assembly. We will cover them in class, but in order to follow me, you will have to do this. But again, not super hard, because, and again, GDB, like the way you will have to debug in this classes will be single stepping instructions sometimes. But again, I will help with that. So like people ask me how to succeed in this class, and the answer is read the source, right? So in the end, again, remember I started saying that it was inspired by MIT. The class name was Operating System Engineering. Their first opening paragraph was something like, it's learning by doing, right? So here it's also learning by doing. So it's very concrete class. So, and in order to succeed, you will have to read the source code. My favorite anecdote, I used to have a student here in this class, and he was later worked for me as well. He was an undergrad, very bright. And my TAs were saying, like some question, some challenging question on the exam. Everyone is searching Google. Back then it was allowed. There is no answer on Google. Not surprising. And that person was essentially reading through the source code. So during the exam, I asked a question. The person a priori might never, like maybe he read it before, maybe not. But in order to answer the question precisely, or this specific question, he was reading the source code, and that gave him the correct answer. So, and it's totally doable, and it's a very useful skill. So I have another anecdote skill. I have a friend who became, let's say, a CTO or some kind of like higher end position, because at some point, no one in the company was willing to commit to certain parts of the code. No one understood what it was doing. Took essentially the effort to read through the like layers of whatever people wrote before him, and then was able to do those commits, which potentially can break the entire system, right? So it's a useful skill to read the source code. Okay, how to succeed continued. As I said multiple times, the class is relatively hard. Again, don't worry about the grades. Grades are always good in this class. I don't see another way of like kind of teaching it without cheating or being dishonest to you, essentially. If I know how to do it, I believe I can teach you, so you will learn as well. But again, I would say nothing to worry about. So that's the end of my logistic part. So any questions? All good? Yeah.
Do you know about?
Well, in a couple of hours. Wow. Yeah. I have to figure out how, again, university allows me to invite you on Piazza and stuff like that. So, but that should be easy. Maybe like half an hour. Okay, good. Enough with logistic. Everyone is happy. Okay, now let's switch. We still have, I forgot. I finished at 30 minutes past the hour, right? So 30 more minutes. So let me switch a slide deck, and it's finally we're getting to something more interesting. So this one is an attempt to show you a black screen. How we do this, I actually don't know. Do you guys know how? How can I say show everything? Use slideshow. This one. Switch to PowerPoint. No. PowerPoint doesn't want me. That's back to the previous slide deck. Let's try again. Presenter view. Play from the start. Nope. Swap displays. This one. Man. Now what do I have? Is it because say again? It was good? Oh, it was good for a sec. Okay, thank you. Yeah. But it disappeared for me. You see it still. Oh, wow, cool. So how do we do this? How do I get my mouse there? Let's start again. Man, really? That has to be that hard. Used to run Linux for many years, and then I get tired. Who can guess why I switched to macOS? One single reason. It's actually so so absurd. So why and don't play video games. Can you play video games on Mac? Cool. But I don't care. Screen recording. No, actually it was weird because Zoom does not optimize for Linux, but in the end, it worked. Other reasons. There was another. Yeah, that's the reason why I switched to macOS. But why did I switch from Linux? Cheaper, you mean? MacBook is cheaper. Well, it's not cheaper. It's a good piece of hardware, that's for real. So maybe quality for the price is actually acceptable, I agree. But there is one reason which is so it's just 2 words. But okay, you said, okay, what's now? What is this? Why am I it doesn't allow me to go to the other screen. So how do I switch? My mouse in the screen. Okay, and switch desktops or swap. Oh, success. Well, hopefully never get. Okay, the answer is one thing, power management, believe it or not. So when I used to run first IBM laptops, right? Those black machines. Then I used to run Lenovo laptops. And gradually, combination of hardware and software stack. Hardware is Intel because Intel kind of screwed out power management. But then software itself, Linux itself, does not optimize that well for power management. Out of Mac, I can get whatever, many hours of work. Don't have to worry about it. And it's the only reason. Everything else kind of annoys me more. Okay, sorry, back to the subject. Enough. So I will spend this 30 minutes. Probably I will run out of time, but I will try to convince you. Why would someone like you do an operating system class today? Because intuitively, it feels like everyone should do machine learning and AI, right? Because that's what pays money. Totally agree. But maybe there is a chance to get some money out of operating system class. So hold on. Let me ask you a question, my interactive style. So why do you think we have to learn operating systems? Or, I'm not asking it in some abstract way. I'll tell you another anecdote. I used to have a student, again, undergraduate, BSMS, right? And what he was doing, he was buying I keep telling this anecdote, so you probably heard it from me. So he used to buy the newest phone from Google, whichever they release every year. And then he was a bounty hunter. And he was actually making money on submitting vulnerabilities to Google. He said, but that in a couple of years, he made roughly 80K. which is a decent amount if you work alone. Because if you work as a team, you know, well-funded by some international government, you know, then it's a different story. He was working alone or sometimes with a buddy. And it's pretty impressive, right? So that's a concrete skill. So he knew enough about Android kernel, Linux, and when, you know, Samsung or Google releases a phone with new device drivers, which manage new hardware, new modems, stuff like that, new screen, he was finding bugs in those and submitting them to Google. Google was paying him bounty. He has a successful career in industry. I think he has some kind of a higher up position in Qualcomm as a security researcher. So that's one reason. And this is what I was trying to kind of like, not some abstract reason, but a tangible reason. Why would someone do it for the sake of getting some benefit out of it? So what would you guess? What's the question? Why are you in this class? So are you like, okay, if it's a required class, I get it. But even if it's so, do you think you can benefit from this knowledge to make some money or do something useful with your career? There was a hand.
Yeah, you'll know better vulnerabilities, like what crashes for security.
Right, exactly. That's one big reason, especially before the AI boom, security was paying quite well, actually. Why is that? And it's part of my slide deck. In 2 seconds, I will switch to it. But really, security was a big deal. Like, we were building the systems which, as of today, root back 50 years ago, and they're completely insecure. And especially with the advancement in automated analysis tools, you can find those vulnerabilities and exploit almost everything what is here around us, which is kind of scary. So security is there, right? So reason number one, I agree with you. What's the reason number two?
People are still writing operating systems.
Why would they? So tell me, why do you think they do this? What are the reasons? They don't do anything. Like, look, Android, we use Linux kernel. Now they're writing something. What is it?
For new hardware or to take advantage of accelerators.
Correct. Right. So my second part of this slide deck is actually performance. So it's true that if we don't even write completely clean slate operating systems, we modify them to adjust to new hardware. And the hardware kind of driving us forward, saying, okay, look, if you want to win the game, and sometimes, 10% of performance translates, if you run the whole data center, that translates into millions of dollars, right, over time. So, and sometimes you do write for new hardware, but also you have to understand what the operating system is doing underneath to make sure that your software is running fast, right? I'm more interested in building something new for new hardware and kind of understand why kind of like push us forward for real. But like pragmatically, yes, if you want to write fast code, you have to understand not only how CPU works, so like that's also needed, but also how operating system works and how these layers of runtimes in the language work for you as well. But it kind of roots into operating systems because it's the base layer. And if you don't understand how it works, it's hard. Okay, so security and performance, those are two good enough reasons. So, and I essentially half of my slide deck here is about security and half of is about performance. So the problem which we have today is that, as I said, each of us has a kind of a Unix kernel in our pocket, right? Android, iOS, macOS. But really, it's the same system which was developed 40 years ago. And so these two guys here, so Ken Thompson and Dennis Ritchie here, building the first Unix kernel, right? And it looks very similar to this x86, which I mentioned before, right? So we'll take a look at it later. But that's essentially the problem. Like 40 years later, we still teach the same kernel and we still run it, but the world has changed, right? So we're no longer like running it in one expensive machine. We're running data centers, right? And it's, again, every application of this phone runs in a data center somewhere, right? So that's essentially data centers kind of enabled mobile applications, right? So nothing runs on the phone, everything runs somewhere else, right? Again, everything on this screen runs an operating system kernel. In fact, it runs Linux, I think. A couple of good examples. There are cars which run Linux. And this is an old slide, but these days there are more exciting electric cars which run operating systems. And it's kind of like, it used to be in the past that a car comes with, let's say, 100 microcontrollers. It's expensive to build firmware, maintain hardware. Now they say, look, we're going to buy one board. It will run some kind of a hypervisor, which will be context switching with certain guarantees between those different software stacks. And it's kind of software-defined car, right? So, and that's cheaper. But a lot of those things like run operating systems, right? And if the first system, remember I said it was similar to x86, so roughly 10,000 lines of code, modern Linuxes are, well, millions of lines of code. So again, roughly depending on how you count, it's 27 million lines of code. If you believe that any person in the world can understand 27 million lines of code, it's kind of a naive assumption, right? So there is not a single person which has a complete knowledge of Linux, which means that certain assumptions are broken. You know, I wrote some interface, I assumed X, Y, and Z, you write against it, you break the assumption, we have a vulnerability, right? And sometimes, you know, vulnerabilities can be relatively easy, right? So let me show you like the count by years, right? We used to live in the environment in which, you know, no one really cared. I don't even have the tail from 2005. But at some point, people said, okay, we can easily find hundreds of vulnerabilities in the Linux kernel, right? And there is a constant kind of like game saying, okay, the researchers will try to build the tools to detect those vulnerabilities and fix them. But in practice, it doesn't work this way. So the kernels remain vulnerable. So it's easy to have like a couple of hundreds of vulnerabilities in the kernel. And okay, when I say a vulnerability, what does it again means in tangible terms? Why is that bad? So who can tell me? Correct. And if I'm like an attacker, what would I go after? What would I read? Correct. Right. So in the end goal, I mean, there are different goals, but often it's driven by gaining some financial benefit, right? So I can break into your bank account because I was maybe reading the memory because I first broke into the operating system kernel. Then I get access to the memory of the process which runs, let's say, Firefox, and you sign in into your Bank of America account or something like that. And suddenly I know your credentials. Or maybe even simpler, I will just install something what will log every keystroke in the system. And then eventually I figure out what you typed and get all credentials, right? Or break into your web browser, read all the passwords from the password manager, right? So, and it's kind of, it's the reality of life. So this is very practical today. Vulnerabilities can be as simple as this. This is the beauty of C, right? So there is like this tiny symbol. There are two data, like there's a data structure and there's a pointer to the data structure here. And someone here in this code, instead of like saying, take the address of the data structure, which is a correct code in green, says to take the address of the pointer. And it's just gives you write primitive. So you can write into memory or maybe read primitive and you can read into memory. What's interesting is this vulnerability existed for at least 3 years, right? In Linux kernel from version 3 to version 3.13. And now they're just to scare you a little bit more. It's a remote exploit. So I can send you a well-crafted packet and, you know, I own your machine after that. And so, you know, like you say, we at least need to understand what's going on in the operating system kernel in order to make it better. What I'm claiming here in this class is that I don't think it's possible to patch Linux. With all the security tools we will be able to invent, I don't think Linux will become bulletproof in any feasible amount of time. So all the systems are exploitable. And so one way to essentially try to change this game is to start building operating systems from scratch. And again, we'll learn one small microkernel, this x86 or Unix kernel, but maybe you take it forward and then in your life say, okay, now I will work for the company which will be building these new operating system kernels. And for example, the way which we were building a couple of years ago, it was called Redleaf. It was essentially combining two ideas. One is language safety, so Rust. Essentially, someone mentioned that C is unsafe, Rust is safe. So in Rust, you cannot just make up a pointer out of nowhere. So this bug, which I was showing you on the previous screen, is just essentially caught by the language compiler. The code refuses to compile, right? So this is useful. And I'll show you in a second how many vulnerabilities can be addressed by just using Rust. But also we were using a step forward. So we were using something what is called formal verification. So it's an idea which allows you to build mathematical proofs about your code. So essentially you say, here's a high-level model. I believe that this and this happens when the kernel receives the packet, network packet. And my actual code implementation actually corresponds to this high-level specification. And it used to be very, very hard or even infeasible. But in the last couple of years or 5 years, those ideas of formal verification became feasible. And if you know the kernel, you need to know everything, right? And then you can actually apply those tools and make sure that you can build kernels which are guaranteed to be bulletproof, right? Anyone knows what is so special about Rust by any chance? Good. So how many people in the class understand this idea of a borrow checker? Maybe a dozen, right? So again, I'm not saying that you are way behind on it, but Rust is a useful systems language, right? It's right before the AI ML boom, which happened was ChatGPT a year ago, roughly, right? So people were hired by just the fact that they understand and can code in Rust. Kind of argue that maybe it's useful. The idea is actually very, very simple. So in Java, imagine you have a context, let's say a function, right? So you allocate an object on the heap, right? So this vector. And in Java, you can pass the pointer to this object around, right? So to another function or another thread of execution B, right? And in when A goes out of scope, you finish that. The question is does anyone still has a pointer into this object on a heap, right? At what point it's safe to deallocate? In C, there are no those questions. In C, you can deallocate anytime, and then you will have a dangling pointer. But in Java, they run something what is called the garbage collector, and it essentially reasons about the whole heap and says, okay, there are no other pointers into this object. At this point, it's safe to deallocate, right? But it's expensive to run this garbage collector, right? And Rust introduced this idea, which wasn't new to Rust, but it essentially was kind of Rust made it practical. Before Rust, it was just impossible to use. And in Rust, it's kind of possible, almost. But as you can guess, it's not as easy. But essentially in Rust, if you allocate an object, if you pass it around, you automatically lose access. If you try to dereference the object again, the type system tells you, okay, you don't have a right, code doesn't compile. But what it gives you is that you have a guarantee that when the B goes out of scope, it's safe to deallocate the object, right? And surprisingly powerful idea. So, and I understand that it's a detour, but let's just, surprisingly, the code remains almost as fast as C. There is no garbage collection. So it's and it's reasonably transparent, right? So this is the plot of implementing a device driver in 10 different languages, starting from Python and going up to C. So C is this black line at the top. Obviously, it's the fastest because it's almost like assembly, right? So unless you have a very clever compiler which optimizes better than you write in assembly, your code in C will be the fastest. And typically, if you take a language, something like C#, which is, let's say, one of the fastest managed runtimes, it still loses 40 to 36% performance, right? And if you take a Rust, then it comes much closer to C. There's still some performance loss, but not horrible, right? So, and I told you, okay, we have this hundreds of vulnerabilities in Rust. And this is another diagram from Microsoft Research, which says, okay, like we analyze all the root causes of those vulnerabilities. And it turns out, like how we're gonna read this plot, like this, the dark blue at the top is like vulnerabilities on the stack. Oh, sorry, like this light blue is vulnerabilities on the stack. We're gonna talk in this class about stack. I will explain you what it means to call a function, right? So what happens to the stack? Why? Because when we will have to load something in memory, like a process, and run it, obviously it doesn't run without a stack. Same for the operating system kernel. Like when you boot on bare metal, you have to get the stack from somewhere, right? And so you say, look, there is a good progress on eliminating those vulnerabilities on the stack. They're almost non-existent anymore in 2018, right? But they used to be a big problem. So the next category here is vulnerabilities on the heap. This is similar to what I was showing this before, like where you allocate an object and then you incorrectly reason about whether you still have references into this object and you deallocate it or do something, or and then incorrectly read memory. They are not going away. They're still here around. U*3 is one of those examples where you deallocate an object and still try to dereference, right? And so we go on, and it turns out that everything but other can be eliminated by Rust. So roughly speaking, 70% of vulnerabilities can disappear if you just rewrite your code in Rust. That's a powerful idea. Industry understood it just a couple of years ago. I mean, there was kind of like academic buildup. Us researchers were trying to convince everyone that first, like people who build Rust, Mozilla Foundation, right? Then people who started using Rust, like us, like my research team, to build kernels. And then eventually industry said, okay, look, it's clever, you know, like we are like out of 100 vulnerabilities, we'll have only 30. It's money to them. So the takeaway here is that, yes, so you have to understand everything to be able to even reason about this plot, right? So those vulnerabilities, what is heap, what is stack? You have to understand operating systems. And ideally, if you want to really be on top of things, you will be building your own, a better one in better tools, throwing away Linux, building a new one, right? So from this class, you can like get beginnings of this knowledge and then build up on it, like build a career out of it. Let me, since I have still 5 minutes, right? Let me quickly, and we build a system which is called Redleaf, which uses those ideas, supposedly better, exploitable like hell. Don't believe us, you know, because it's me and my students, you know, anyone can exploit it. But if you take serious people on board, then you can make it better. And the second problem which I was talking about was performance, right? So, and it's understanding of how the world will look in 5 to 10 years, right? And again, a lot will change. You know, you will get better ML frameworks, but if you want to make them fast, you have to learn how to build operating systems for them. So for decades, again, five decades, essentially our system looked like that. So there was a single CPU, potentially has multiple logical threads, then multiple cores, right? So now we have machines with whatever, like 80 logical threads or even more, right? Then devices were attached to the CPU. We had memory, we had bus, which was connected to peripheral devices like disks, and maybe like a faster disk, it's a network, this network interfaces, right? And maybe quad socket machine, right? I don't know if you ever seen one. So, but this one, like a quad socket. So essentially, it's just a blade server, like 2 CPUs sits on top of another 2. And then you assemble a data center. This one is Emulab, which is in the, what is it? Merrill Engineering Building, 3rd floor. Looks like that. You can take a look, right? But you ask yourself a question, okay, I want to run real fast ML workloads. Is that a good architecture? And this is still what we're doing. But if you think about it, so maybe it's actually not the best hardware setup for running those things, because typically you have tons of data and data sits on disks. You have tons of networking traffic and it comes through those network interfaces. But in order to do something with this flow of information, both from disks and from network, you have to push it to the CPU, right? And execute it on the CPU and then maybe push it back to the network. Feels a little redundant and takes time actually, right? And so people started building machines which are slightly different. So they essentially say, look, instead of like pushing all the workloads to a single CPU, we'll come up with various accelerators. And someone was mentioning this idea essentially when I was asking a question like, yes. So, and the idea is that you can, instead of pushing data to computation, you can somehow combine both and either move computation to data or just do a hybrid, essentially. Sometimes data moves, sometimes computation moves, right? But essentially your machine will be a collection of those accelerators. Essentially here, I say there might be some memory. And we see these ideas, right? So you've heard those words, so disaggregated memories, right? Essentially, it's in a data center. One machine has minimal local memory. Another machine is packed with tons of memory, and there is just a fast interconnect between the two. And this way, you don't have to like buy every blade server with like gigabytes of memory. You just have a terabyte somewhere. And there is an interconnect showing like essentially like connections between different accelerators. So this is some computation can be executed on a network interface itself. We say, look, I'm going to be filtering network packets. Maybe I'm detecting intrusions or something. The question is like, is it possible to do today? Like, because the operating system, which we usually use, they run on general CPUs, but now you say, look, part of my logic of my program has to run on this near network core, right? And so on. So you will have programmable cores like FPGAs, AI accelerators, which you're probably all excited about, right? Because this is real money. If you know how to deal with them, you make money. There are like some cores near storage, essentially. As I said, don't push data to computation. Move computation to data. It's done in modern database accelerator startups. Essentially, instead of like you compile an SQL query, and part of this SQL query executes on the accelerator itself, on the like next to the data. It's much faster because you can pre-filter what you actually process later. And essentially the question here is that, is it possible to build an operating system for it and how it will look like? What is even abstraction of a process? And I understand, okay, I didn't even explain what is abstraction of a process, but naively you can think, okay, it runs on the CPU, but here it runs somewhere else. And it's not trivial to answer those questions. And so again, by taking this class, hopefully 5 years later, you will be able to participate in this game of developing software, which is designed for those machines. Okay, so let me stop here because we're out of time and it's a good stop. So good point. So next time we're gonna start, I will do an introduction, explain what operating system is about, and then we will move forward from there. Thank you, guys.